All right, hello everyone. This is Mr. Lee. In this video, we are going to go through charging a capacitor. We're going to derive the current equation. All right, let's begin. So hopefully in class we looked over the capacitor and the properties of a capacitor as it was charging up. But just in case you are watching this video without having done that, let's just do a quick little discussion. All right, so we have our EMF source here, and we had in class I used a light bulb, but it's just a resistor here, and we connected it to a capacitor like so, okay? And we probably put a switch in there, like right around here, so that we could turn it on and off. And so at time equals 0, the switch is off, okay? And at time is equal to infinity, the switch is on for a long time. All right, so I want to start off there because when the switch is just turned on, or t equals 0.00000001 seconds, very important things happen. And for the rest of the video, we're going to be referencing these ideas. Okay, so a couple of very important things. One, there's no charge in the capacitor because we didn't start charging it up yet. But here's the important thing. The Q will fill the capacitor, right? So we know that eventually as time passes on, the capacitor will start to fill up. And so I guess with time. So the important thing about this is that we're going to be talking about everything with respect to time. So the charge will fill the capacitor with respect to time. And so for those of you with a savvy little mind, you'll hear that that is just Q over T, which is current, right? And so that says that the capacitor will have a current when time passes on. Okay, but we want to see how that current changes with respect to time. And so one of the things that we saw that in the classroom is that the current in the capacitor is going to be, I guess, max right at the beginning. And that approaches to the current to be 0 as time continues on and on and on. All right. And this is because here, this will be a filling up of charge on the capacitor. Okay, so we're filling it up, we're filling it up, we're filling up. Here we have max Q on the capacitor. Okay, and so this is where it's where the switch has been on for a very long time. So the idea is if you can no longer put charges on the capacitor, you're not able to put, there's no more charges per time, so therefore there is no more current. All right, so with this here, we can say at time is equal to 0, the capacitor acts as if it is a wire, okay? Or you could think of it as your resistance is 0, right? It allows for charges to flow freely, but as time approaches infinity, the capacitor acts as a broken wire, okay, where the resistance is infinity, meaning that you're no longer allowing charges to move. So like a broken wire or a resistance of infinity, right there, there's no movement. And so with this here, we can say that the at time of 0, the capacitor has a voltage. So at time of 0, the capacitor has a voltage of 0 volts. And the reason why we can say this is because the formula for a voltage of a capacitor is charge per capacitance, right? So it's how much the capacitor can hold. So if you don't have any charges, so because Q is 0 coulombs at time 0, but as time approaches infinity, the capacitor has, we're just going to say max Q, and we're just going to represent that as a capital Q. And so we can say that the capacitor has a voltage of VC, or and in our case, it's going to be the max EMF. Okay, so the EMF source, the max voltage. All right, so a couple of very important things to take into consideration because we're talking about time. And of course, when we're talking about time, that's where the fun begins because we can now do some calculus, right? So a couple of things that I want to put off on the side so that we can reference it as a highlight. The voltage for a capacitor equation is Q over C that we see over here. Let's highlight that so that I can quickly see it. We know that current is equal to charge per time. But for here, we see that the current is changing because the amount of charge that is moving is changing. So I'm going to represent that as I is equal to Q over T, right? Lowercase I. It's just a fancier way of saying that it is a changing current. Let's see, one more thing. We can say that EMF is equal to IR, where I is the total current, R is the total resistance, and that is the EMF source. This is Ohm's law. All right. So with that, we want to try to prove the following. Okay, so let's go back to these bullet points here. So we said that at time 0, it acts as a wire, and R is equal to 0. And so here we have max current. Okay, and at time is at infinity, the capacitor acts as a broken wire, so R is equal to infinity ohms, and so we have no currents. Right, so we wanna prove this, and also if we are at time of 0, that means the capacitor is fully charged. Okay, so now we're talking about this down here. So we want to prove that we have Vmax, which is just equal to the EMF source, and in time of 0, we have no charges on the capacitance, so we can say that the voltage of the capacitor is equal to 0 volts. Time is 0. Okay, so these are the couple of things that we want to try to prove because we want to see that our math is right and our calculus is right to prove the laws of physics. It gives us a goal. It's pretty fun. I enjoy this stuff very much. All right, so with the things that we said before, let's just come up with a couple of formulas to start us off. I want to have a thicker pen. We said that at, let's see, time of infinity, the EMF source is strictly in the capacitor, so VC, and if we refer back to the formula, we said VC is equal to Q over C, okay? Meaning that because it's fully charged up, there's no current flowing through the resistor, and so the resistor doesn't have any of that voltage there. But here at time of 0, our EMF source is fully devoted to that resistor, so that's the IR. And the reason why the capacitor doesn't have any voltage there is because it doesn't have any charge, right? There's no charge, therefore 0 over C gives us 0. All right, so this is the two extremes. And so what we want to do with the power of calculus, what happens in the middle? So this is the beginning of our journey. This is the charging up. All right, buckle up, put on your calculus caps. Let's do this. All right. So a couple important things. So as t goes from 0 seconds and it approaches infinity seconds, for a charging up, the voltage for the capacitor increases while the voltage from the resistor, it decreases. Okay, and at the two extremes, the capacitor will reach a voltage of the EMF source, and at the other extreme, the voltage of the resistor will reach a voltage of 0 volts. Okay, so that's a very important distinction because in the next video we're going to do a discharge, and the discharge has the opposite. All right, so what we're going to do is we're going to try to come up with another formula that resembles a lot like that, but because those are the two extremes, we want to see what happens in the middle. Okay, so we can say that the total EMF is comprised of both the voltage of the capacitor, okay, plus the voltage of the resistor. But what I want to do here is I want to substitute in the voltage of the capacitor formula, which we highlighted above, Q over C. And the voltage of a resistor will be IR. But see what I do here? I'm going to use the lowercase I simply because the current is changing. It's not constant. And we could also, I'll do this appropriately. That Q should be a lowercase q, I'm sorry, because the amount of charge is also changing. Okay. All right. So the whole point of this video is to derive a formula for the current equation. And so what I want to do is I want to rearrange my formula algebraically so that we have a function of I is equal to. And I'm assuming that your algebra is spot on, and you should get I is equal to the EMF minus Q over C, all divided by the resistor, right? And the resistor is constant, so we're leaving that as an uppercase to show that as a constant. This looks pretty ugly, so I want to clean this up and say that the EMF epsilon divided by R minus Q over RC. Whoa, would you look at that? So if you ever see the term RC circuits, it stands for resistor capacitor circuits, RC. All right, so this is the term that we're going to work with. I is equal to all of that. Now, at this point, you're going to have to just trust me here. This is a leap of faith. We are going to factor out, what are we going to factor out? Let's see, negative 1 over RC. Now, I can give you a reason as to why we're going to factor out R and C. Well, those are our two constants, okay, and that'll just make our math a little bit easier. But the leap of faith of y is the negative 1 R over C. Well, RC is in the denominator. But 2, this comes very handy mathematically later on, and that's just me knowing what the future looks like. So you just got to trust me on that. Okay, and so because we're looking at the change of charges per current, right? So I equals dq over dt. So we say dq over dt. So if you're wondering where I got that, this is a changing current, and a changing current is the changing amount of charges moving per time, okay, is equal to, so remember I factored out negative 1 over RC, and hopefully your math is correcto. We get negative epsilon C plus Q. I just gotta make sure I don't make a mistake. So I'm gonna rearrange that inside part so that it looks like this. Yeah, that makes my math brain happier. All right. So we have all this, and at this point, what we want to do is we want to connect our like terms. So here we have the dq, and we have a q over here. So I want to make all of the terms with the q on the same side. I'm going to move everything else on the other side. So if you do that, I'm going to divide both sides by this parentheses factor there. So we get q minus epsilon c is equal to negative 1 r over c times dt. Right? And you can even write this as negative dt over rc, but I'm going to leave it like that because that's going to make my integral a little bit easier. So this step into the next step, I'm going to integrate both sides. Let's do this in a beautiful blue so that you can see that I just skipped the step there. And from here, I'm going from no charge all the way up to a total charge. And total charge for us will just be that capital Q. And so from here, we're going from no time to time, right? So whatever time it takes to maximally charge this up. All right. And according to the rules of calculus, whenever you do dq or dx over something, we get the natural log of that something, q minus epsilon c bounds 0 to the q, and over on the right hand side, that negative 1 r over c is a constant. Yeah. But the integral of dt with respect to 0 to t just gives us negative t over rc. All right. Now this is where it gets a little bit fun/tricky, and you need to know the rules of calculus here. So here are the bounds. Let's plug in our bounds. So we get ln of capital Q minus epsilon c minus natural log of, we're going to put a 0 in for that lowercase q, but we still get negative epsilon c, right, is equal to negative t over rc on the right-hand side. Now here's where the rules of natural logs come to place. If you have two natural logs and you're subtracting them, technically what you're doing is you are actually dividing the two, right? So we get natural log of capital Q minus epsilon c over negative epsilon c is equal to negative t over rc. Keep your rules in check. Keeps your math in check here as well. So we don't like that natural log. We want to get rid of it. The only way to get rid of natural log is to raise everything up by do e to the power of all that. So when we do that, we get we can clean this up using the rules of math, and we get q minus this all over this is equal to e to the power of negative t over rc. And just so that I don't make any mistakes here, I wanna clean up the left-hand side. So we get negative q over ec plus 1 is equal to the right-hand side. Okay. Now I want to have this as a function of q. Okay. Because current is in terms of charge. And so we get negative q over epsilon c equals negative 1 plus this. And my final step, I want a function in terms of q. So I'm going to multiply everything by negative epsilon c. All right, so that single-handedly gets rid of the negative sign and that denominator there. And so we get q is equal to epsilon c minus, let me do this appropriately. Negative 1 plus e negative t all over rc. All right. The only thing I want to do with this inside function, I'm just going to distribute that negative so that I just get this here. Why, you're wondering? Well, I know the final answer is, and it's just clean math, right? And that's what we want. Okay, now we're not done yet, because if you take a look here, this epsilon c, if you remember all the way at the beginning, I said that's going to be one of the formulas that we're going to need. It's this formula right there. Instead of using v, we use epsilon. So we can substitute that back in. Yeah. So here we have a substitution where this is simply q final. All right. Q final is equal to 1 minus. Yeah. Okay. Woo! If you got this far, applause for you. You did some awesome mathematical gymnastics. Oh, that becomes our formula, but let's actually define what the variables mean, okay? Because we have a lot of variables that look very similar with different subscripts. So this Q is going to be the total charge on capacitor, okay, at time t, right? So that could be any time. It could be time 1 second, 2 seconds, infinity seconds, whatever that time is. This QF is the total charge allowed on capacitor. So that's max charge. Okay. And I wanted to make that distinction between QF versus just regular Q. That regular Q is there to show how much charge is on the capacitor at the time. QF is the maximum amount. That T is just time. R is the resistor. Okay, once again, the resistor in the circuit is a constant, and C is the capacitance. Okay, how much the capacitor can hold. All right, so yeah, we have that formula, and that's good and all. But now, with this formula, let's come up with the voltage formula. Okay, so this is going to be the voltage for the capacitor at any moment of time. So we know from our formulas that we highlighted above that voltage for the capacitor is equal to however amount of charge on it over the capacitance. So what I wanted to show you, this is a cool little trick, is we see that voltage and charge are directly proportional. Now, here's a cool little nifty trick. Because they're directly proportional, we can take the formula above and just replace all the Q's with V for voltage. And so if you do that, we get, let's see here, V as in V, the voltage at a moment of time. So I guess VT is the proper way of doing it. V naught, where V naught is going to be the total amount of voltage that it can hold. 1 minus e to the negative t all over RC. Okay, so that is the voltage formula, and we got that from the derivation of the charge formula. And we're almost there. I wanted to prove a couple of things. We got to get the derivations first before we prove anything. So the next thing that we're going to do is using our charge formula, we're going to derive the current formula. Okay, so I know I got rid of it, but I'm going to rewrite the charge formula down here. What is it? We got Q is equal to Q final times 1 minus e to the negative t all over RC. All right, now here's a couple of big jumps that we have to make. All right, one of the things is that we said that the changing current is the changing amount of charge over a moment of time. Okay, so we are going to use that, but we're going to rewrite this so that it looks like this. Because based off the function that we have, the function that we have is the amount of charge per unit of time, all with a respective time. So what this means is that anything with a variable of t in it is what we can derive, and everything else is considered to be a constant. And so that helps us out because you see that QF right there. That QF is considered to be a constant, so we don't have to do any fancy derivatives with that. So if we derive this formula here with respect to time, now just as a reminder here, this is a time derivative, right? We're taking everything with respect to time. What we end up with is the current, okay, at any moment of time is equal to negative QF e to the negative t over RC, but thanks to the chain rule, we also have to multiply that by negative 1 over RC. And if we clean that up, we get QF over, positive QF, negative times negative gives us positive, over RC, e to the negative t over RC. Now, for those of you with shrewd eyes, okay, you can see that this QF, okay, this QF, using one of the formulas that I gave you above, we know that the voltage for a capacitor is equal to charge per capacitance. Okay, so if I rearrange this, I get Q is equal to VC times C. So if I plug that, if I substitute that in, if you're wondering where I'm substituting that in for there, we get the voltage for the capacitor times C over RC e to the negative t over RC. And this, the C's or the capacitance do cancel out. So that gives us voltage over R, okay, times e to the negative t over RC. Now, once again, we can clean this up again. And that's what's really cool about this because of Ohm's law. Ohm's law is V equals IR. And for our circuit here, we said that our V total is epsilon IR. And would you look at that? Here is the substitution for I. So we can say that I, with respect to time, is equal to I total e to the negative t over RC. Wow! So we have here our three different derivations, that we got all from the circuit. So now we have to actually prove that all of this is correct. And yeah, that should take no time at all. So the first thing that we want to do is let's take a look at this current formula. Okay, we said that when time is equal to 0 seconds, okay, the current is at its max. Okay, so if we plug in I of 0 is equal to IT e to the 0 over RC, e to the 0th power just gives you 1. So what this shows us is that the current at time 0 is equal to the max current or the total current, right? And just like that, we can take a look at it when t equals equal to infinity. We said that when t is equal to infinity, that the current is 0. So let's plug that in. So we get IT e to the negative infinity all over RC, okay? E to the negative infinity, right? That gives us a big fat 0, right? And 0 times IT, excuse me, that should be infinity, gives us 0 amps. Wow. So what this shows us is that when a capacitor is fully charged up, there is no current flowing through it. Now, what about the voltage, you might ask? So the voltage, if we take a look at the voltage formula, let's see here, we see that Vt equals V naught 1 minus e to the negative t over RC, right? We said that when time is equal to 0, the voltage, because there's no charge on the capacitor, the voltage should be 0 volts. So let's see if that's true. V of 0 is equal to V naught times 1 minus e to the 0th power. E to the 0th power is just 1. 1 minus 1 gives us 0. V naught times 0 gives us 0 volts. Oh my gosh. If that's not cool, I don't know what is. All right, the other thing that we can prove is that when t is equal to infinity, we said that the voltage of the capacitor is equal to the total EMF of the source. So let's prove that to be true. V of t is equal to V naught 1 minus e to the negative infinity all over RC. E to the negative infinity simply gives us 0. 1 minus 0 gives us 1. 1 times V naught gives us, whoa, right? And so V naught is our EMF source. Would you look at that? Now, if that's not cool, I don't know what is. That is spectacular, having the time of my life over here. All right, so that's our proof. We proved it. Okay, so we can see that what happens to the capacitor at time 0 and time infinity when charging up. Now, the very last thing I'm going to point out is what we call tau. Okay, so this is a Greek letter tau. I think T-A-U, right? This was the same variable that we used for torque. Okay, but when it comes with capacitors, we're not talking about torque. We're talking about the time constant. So this is called the time constant. And the time constant, it is equal to RC. So the resistor times the capacitance. Okay, and so what the time constant tells us, it is the amount of time to charge up or to discharge. Okay? And usually time constants come in with respect to like fives. Okay, so what I mean by that is when you look at a graph of a capacitor charging up, you split it up into fifths. Okay, but the important thing here is that 1 tau is equal to, what do we have here? So it is 63.2% of either charging up to its max is 1 tau, or 36.8% of depleting. Okay, and this is when you're discharging it. And so here, this gives us 1 minus e to the negative 1, and 36.8 is e to the negative 1. And so this right here, we see that as we take a look here, right, in our formulas, we see that 1 to the 1 minus e to the negative ones all over the place. All right, and that's that for capacitors. This is for charging up. We will go over the discharge later. Bye-bye.